All right, so you watched the demonstration with the graduated cylinders and the colored water, and then hopefully you went and you answered the questions that were about that. So what we're going to do is talk about the questions that you answered to an equilibrium simulation with water, the graduated cylinders. So on the back, you had to do questions 1 through 5, and then I want to go through those. I want to do a little bit more to make sure you're comfortable with things. So in our simulation of a reversible reaction, when did you know that the system has actually reached equilibrium? Or I should say, how did I know that the system had reached equilibrium? I looked and saw that the numbers in the graduated cylinders stopped changing. So it's not that they were equal, it's that they were constant. So the way I knew is that the volume of the graduated cylinders were constant. Okay? They stopped, the volumes stopped changing. Okay? They weren't equal, but they were constant. What was equal when the system reached equilibrium is something that I couldn't see directly to know that I was at equilibrium. I had to prove it with that last step. So that last step is where I measured the volumes in the 2 straws. So the volumes in the straws is what was equal. The amount of liquid transferred from A to B was the same as the amount of liquid that transferred from B to A. Okay, why wasn't it at 50 and 50? If you think about it, I had 2 different diameter straws. Okay, so the diameters were like this. So a straw with this diameter is going to pick up a lot more water than a straw with this diameter. So this was A, this was B. Think about what the volumes of A and B were like when we hit equilibrium. A was much lower than B. Does that make sense? You had to have less in A because A was going to pick up a wider area. You had to have more in B because B was going to pick up a smaller area. So that's the only way to get the 2 volumes the same, is to change the height of the liquid that they're picking up. So that leads us into the next idea. Identify the 2 factors that affect the amount of water displaced. Well, one of them is the diameter of the straw. And what's the other one? The height of the liquid in the graduated cylinder. So that's what was changing as we were transferring liquid, the height of the water. Number 4, a chemical reaction reaches equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. What part of the simulation represented the rate? Hopefully you came up with the fact that the water transferred represents the rate. The water transferred between the 2 straws represented the rate. So as soon as the water being transferred was the same, the rates were the same, and so equilibrium was established. Question number 5, most students believed that the chemical reaction is in equilibrium when the concentration of the product is equal to the concentration of the reactants. How many of you predicted that it was going to reach equilibrium at 25 and 25? That's a misconception that I love that you all do, because it really shows that it's not equal, it's constant. So what part of the simulation represented the reactants? So the reactants were what was in graduated cylinder A. We started with 50, it dropped. Products were what was in graduated cylinder B, because it started at 0 and we built some up. Okay? So with those ideas, you can write a paragraph including the ideas that you've got in your discussion. But I want to do one more thing. I want to do a little preview about the next concept, which is Le Chatelier's principle. So let's take a look back at those two graduated cylinders. And I'm trying to remember the volumes. One, A was at something like 18, and B was at something like 29. Okay, so I could have been transferring water forever between those two graduated cylinders and nothing would have changed. But what if I had done this? What if I had added 5 milliliters? And so instead of having 18 in here, what if I had added 5 milliliters of water to graduated cylinder A? So now I have 23. Would the straws now be transferring more liquid or equal liquid? No. What's going to happen? A is going to be transferring more. So the rate of the forward reaction is going to happen faster. So at this point, you've got the forward reaction going much faster than the reverse reaction because the big straw is picking up more water than the little straw is. So what's going to happen? If the straw A is picking up more water, this is going to start to drop. Okay, and if straw B is picking up less water, what's going to happen? This is going to start to go up. And it's going to change until we get to a new point. Maybe I should use a new color. It's going to change until we get to a new point of equilibrium. And so now we have equilibrium being equal once again, once we get these volumes. But notice what's different. We never got back down to 18 milliliters, and we definitely don't have the 29 milliliters anymore. This idea of readjusting the level of the waters in order to establish equilibrium is something called Le Chatelier's principle, or Le Chatelier, as some people say. I just say Le Chatelier. Okay, so Le Chatelier's principle is the next concept that you're going to take a look at. But keep in mind, as you learn Le Chatelier's principle, this idea. What would have happened if I took away water from B? What would have happened if I took away water from A? How will things adjust? How will the rate of the forward and the reverse reaction change? Because one straw is picking up more water than the other straw is now. All right, so your job for this lab now is to finish analysis question number 6. Do a nice, thorough job. I want you to talk about both the simulation and real equilibrium. Don't just focus on the simulation. Transfer that to an equilibrium reaction, and then submit that. All right.